So in this problem, we have a condition a plus b plus c adds up to pi radians. We need to show that cosine squared a plus cosine squared b minus cosine squared c equals to 1 minus 2 times the product of sine a, sine b and cosine c. Let us begin our proof from the left hand side. On the left hand side, we have cosine squared a added to cosine squared b minus cosine squared c. So what we'll do, we're going to keep the first term and the third term intact, but we're going to change the second term, which is cosine squared b, to sine squared b, as given by 1 minus sine squared b minus cosine squared b. Now, what we do, we're going to rearrange the terms to get 1 added to cosine squared a minus sine squared b, and we have the last term, which is negative cosine squared c. The reason why we converted cosine squared to a sine squared function, because that is a standard formula. So our formula being, if we have cosine squared a minus sine squared b, that's going to be equals to the product of two cosine function. One cosine is going to be cosine of a plus b, and the other cosine function is going to be cosine of a minus b. Okay, so this is going to be equals to 1 added to cosine of the angle a plus b multiplied to cosine of the angle a minus b minus we have cosine squared c. Now what we'll do, we are going to change cosine of a plus b to an angle cosine of c. How shall we do that? So we're going to take the help of the condition here. So here we have a plus b plus c, that's equals to pi radians, which means that if we keep a and b on the left hand side and transpose c to the right hand side, we're going to get pi minus c. Now we'll take the cosine function on both sides to get cosine of a plus b equals to cosine of the angle pi minus c. Now cosine of pi minus c, that's simply equals to negative cosine of the angle c. That means, in other words, what we have done is we have showed here that cosine of a plus b, that's the same as negative cosine of c, provided a plus b plus c equals to pi radians. And also here we're getting the negative sign. That's because pi minus c lies in the second quadrant, and in that quadrant the cosine function is always negative. Okay, so let's rewrite our expression. So now what we'll get is 1. So in place of cosine of a plus b, we're going to replace it with cosine of c multiplied to cosine of the angle a minus b minus cosine squared c. So what we do is we are going to take negative cosine c as the common factor from the second and the third term. That leaves us with cosine of a minus b added to the angle cosine of c. So this is going to be equals to 1 minus cosine of angle c multiplied to cosine of angle a minus b. So what we will do here, cosine of c, we're going to change it back to a cosine of a plus b, but we need the negative sign as well. So we have negative cosine of the angle a plus b. Fine. Now we can combine cosine of a minus b minus cosine of a plus b, because again we have a standard formula. So if we have cosine of alpha minus cosine of beta, that's going to be equals to 2 times sine of the angle beta plus alpha over 2 multiplied to sine of the angle beta minus alpha over 2. So here in this case, we'll consider a minus b to be alpha and a plus b to be beta. So let's employ the formula, and that's going to give us 1 minus cosine of angle c multiplied to 2 times sine of angle, we need beta plus alpha. So beta plus alpha, that's going to give us 2 times a divided by 2 multiplied to sine of the angle beta minus alpha, so that's going to give us 2 times b divided by 2. So further simplification is now going to give us 1 minus 2 multiplied to, so sine 2a over a 2, that's simply sine of angle a multiplied to sine of 2b over 2, that's going to be b, so we get sine of angle b, and then finally we have cosine of angle c, and this is exactly the expression on the right hand side. Let's verify it. Oh, we have 1 minus 2 sine a sine b cosine c, 1 minus 2 times sine a sine b cosine c. So thus we have successfully verified that the left hand side equals to the right hand side, hence proved.